Hello, everyone. Okay, let's get starting. My name is Christos Kondopoulos, and I will present today some aspects and some advancements from our project Epipelagic. Um, uh, First of all, I would like to say, as a member and the CTO of Geosystems Hellas, that we are really happy to join this ocean literal festival for the Mediterranean Sea. We are really happy to join this initiative, and we hope that some tools and some perspectives of our projects and of our work in our company will inspire also some other researchers and some engineers, but we'll also find some place for other applications in the field of coastal preservation and the Mediterranean Sea in general. Not I don't want to jump ahead. First things first. I will first have some small introduction of for our company, for Geosystems Hellas, in order for you to know better what we're dealing with, which are our applications, which are our main focus, our main goals in the company, and of course later on we will pass to the specific project that we will be presenting today. As I said, I'm a member for Geosystems Hellas. GSH is an SME established in Athens in 2009. It also participates in a lot of working groups and clusters all around Europe and the globe, participates in international congresses, symposiums, and exhibitions, and we're currently our team consists of around 12 to 14 persons, mostly engineers in the field of geography, geospatial engineering, remote sensing engineering, computing, advanced computing, and artificial intelligence, and etc. Our main activities, our main goal is that first of all we act commercially as Hexagon Geospatial and Hexagon Airborne Solution authorized resellers for Greece and Cyprus. We also participate in commercial service projects for several sectors such as smart applications, automatic processes for Internet of Things, big data analysis and processing chains, and of course some engineering processes such as photogrammetrical, remote sensing applications, geodetic application, surveys via GPS, GNSS, etc. Last but not least, we have a really active R&D department in the last few years. We have numerous R&D projects running right now, more than 15, and we also try to get as much as knowledge as we can from this R&D project, but also we want the final project to be viable and continue their work for the specific case studies we're dealing with. As I said, our core business and expertise deals with remote sensing technologies, geospatial engineering, airborne LiDAR 3D monitoring techniques, and in general, every aspects with geospatial data acquisition and process. And of course, we have some in-house products and services of commercial Hexagon geospatial products, but also we produce and we developed our own software solutions via open source coding. I will later on display some applications that we have developed for the coastal region preservations, but also for environmentally for areas that are environmentally vulnerable and needs more attention and monitor. As I said earlier, what we do is we try to create autonomous remote sensing photogrammetry applications. We also have some big expertise also in the area of 3D monitoring and acquisition of LiDAR and point cloud data, as well as we develop our own web portal and WebGIS solution in order to display any kind of geospatial data we need. We also lately we also tend to connect this information with real-time IoT information, and this is really important and currently in the state of the art. And as I said, we are participating in, we have a really active R&D department. We participate in a lot of R&D projects. These some of the completed R&D project. The first one, English Musa, also deals with the preservation of the coastal region around the northern part of the coast of Greece. So it is something similar that may have a big impact also in the coastline preservation. And this is some of our ongoing R&D projects under the Horizon 2020 framework, and some national R&D projects. Epipelagic project is the expert ingredient support system for coastal mixed urban industrial critical infrastructure monitoring using combined technologies. I will be presenting Epipelagic in a short time. We also currently running an ESA-funded R&D project from the European Space Agency. So this was in a nutshell what's our company's visions and what we're dealing. If there are not any questions, I will proceed with the Epipelagic project presentation. Okay. So, as I said earlier, Epipelagic is a national funded project for Greece and China. It's a bilateral project. So we have partners from Greece and from China, and two specific case studies. So the project has a duration of 3 years. We're currently a little bit later from the middle, so we are in the month 20 of the project. So in about a year, the project should end its activities. What is the problem that we're dealing with in this project is that the coastal, marine, and the riverine ecosystems are affected from the climate change impacts, and in these areas a big amount of population lives, but also these ecosystems usually tend to have a bigger economic impact as well. So conservation and appropriate management of these ecosystems can reduce the risk of coastal flooding, erosion, degradation, and subsidence. So the mission of Epipelagic is that this monitoring, we want to establish a decision support system to efficiently monitor these environmentally vulnerable regions, such as the 2 case studies that we're dealing with. This is the overall Gantt of the Greek site project and the time that we're right now at September of 21. What we're doing in Epipelagic is that first of all we're going to exploit some remote sensing data and applications. As far as the data are concerned, we're going to collect time series multispectral and SAR data from European and Chinese satellites. We're also going to use some other auxiliary data such as geolocation maps, such as Corinne land cover and Corinne land use change maps, and also we're going to to exploit some in situ data such as GPS, GNSS measurements and from an established GNSS network in the area of interest, but also measurements from tight gauges and that are again installed in the area of interest. The result of this is that we're going to fuse all these diverse data from these different sources, both the satellite, the multispectral satellite and SAR data, but also the base maps of the land cover and the in situ information. A data processing paradigm here shows that how we use Sentinel-2 and Sentinel datasets. We define the area of interest, we clip the area of interest from the whole dataset, we proceed to some resizing and resampling techniques, and we create a composite of Sentinel-2 and the Sentinel-1 GRD data. So again, in a nutshell, multispectral data, SAR data, the preprocess is what I showed you in the previous slide of such data. It was just an example. We will fuse all this data in the common Epipelagic database that we have built in, Postgres with a PostGIS extension database. Then we have a component we're calling a knowledge extractor. This knowledge extractor will provide different diverse applications in order to provide different knowledge for our area of interest. For example, from the satellite multispectral dataset, we can provide time series, land use and land cover maps. Or for example, from the SAR analysis, from the ERS and Sentinel-1 SLC SAR data, we can provide DIN SAR maps and for degradation and soil subsidence, but also soil erosion maps. So all this information will be constantly updated with the new data provided to the database, and will finalize to a decision support system with a specific threshold that will provide alerts into a web application that has been already developed. So the scope of this architecture is to constantly analyze information that will feed our database from satellite and in situ data, and produce alerts if an information, if a value, how can I say it, goes in a value that is considered to be higher than the expected amount, to be dangerous for the environment of the Epipelagic case study. So this is in the pyramid. There's the workflow that earlier I presented. Of course, during all these processes, we're going to exploit some machine learning and also deep learning networks, such as the UNet. We also will try to proceed with Transformers neural network in order to provide some information and some knowledge for some future predictions that would be really also interesting. And the decision support system will process data from various sources, as I said, use explainable artificial intelligence methods, and also the crowdsourcing techniques will be considered the threshold values that will be set to the alarm alert system. The Greek case study is the area of northern part of coastal Greece. It is the in Thermaikos Gulf, the wider area of Thermaikos Gulf. Also includes the second biggest city in Greece, is the city of Thessaloniki. But mostly we're dealing with two big river deltas, the river of Aliakmonas here in the west, and in the center the river of Axios. We should also mention that this area of interest, this area of interest is a coastal area, is a Natura 2000 and Ramsar Agreement protected area. Also holds a lot of different diverse species of wildlife, and combines a variety of land uses such as urban, industrial, commercial, and various economic activities. We already performed some field campaigns, and we also saw this slide, I believe. Yes, to this end, we have also made a few publications for Epipelagic. This was in a Greek conference, Elas GIS. We also published this year in EGU for the General Assembly of 2021, and this is the poster of these publications. And we also made two publications in SEMEPE 2021 conference. The first one was about the application of a SWAT model in Aliakmon and Axios rivers catchments for the soil erosion, and the second one was application that we will see today on real time about the assessment of coastline changes in time series data. Thank you very much. This was a brief presentation of the project. About that, if there are not any questions, we can start with the hands-on display, let's say, of the tools, of the remote sensing tools. I have to mention that we have already applied some of these applications in the project, but some applications such as the Python script that I will be showing, we have done it to a secondary also case of study, and we will later on integrate it to the Epipelagic platform and decision support system as I presented. Let me first present the poster of our latest publications for Epipelagic. Mostly is parts and information that I already presented in the few slides previously. And moving on to the tools themselves. Today we will show four different applications for amateur users of remote sensing data and technologies, but also some tools that are more advanced and need some previous knowledge of coding and of remote sensing software. Firstly, we will see how we can access free satellite data in order to perform such applications. It is really important to be able to perform some applications in order to assess information regarding the vulnerability and the environmentally and protect environmentally vulnerable areas such as coastal regions and ocean in general. But it is a different thing and equally important to be able to have our hands on the data that we need to process. The second application will be the coastline extraction via spatial modeling. The third is the coastline extraction via open source solutions. And the fourth application we will see is water quality assessment, again with open access software. In the first scenario of accessing satellite data, we will see how we can get our hands on Sentinel-2 multispectral imagery. In the second study, we will use some spatial models via the commercial remote sensing software RDS Imaging. Later on, we will proceed with some applications via Python scripting for the coastline extraction. And at the end, we will provide instruction on how we can provide water quality maps for coastal regions using Snap tool. Snap is a software for Sentinel missions provided by Copernicus and the European Space Agency. So how we can access the data? There are a lot of different diverse satellite data, commercial and open access. What we will see today is how we can access Sentinel-2 data from the Copernicus Open Access Hub from the European Space Agency. This Open Access Hub provides complete, free and open access to Sentinel-1 missions, Sentinel-2, Sentinel-3 and Sentinel-5. Sentinel-1 missions are mostly SAR data, are only SAR data, let's say, but we can also extract different set of sensors of these missions. We can only extract the GRD products that are the intensity values of the sensor, or we can also get the phase layer and have a complete set of radar technology. The Sentinel-2 missions that we will see today are a multispectral instrument. So there is a passive sensor of 12 different bands. Sentinel-3 mission has also two different bands, two different sensors, and also is really important for coastal and marine environments monitoring. And Sentinel-5 is a mission that mostly deals with atmospheric composition and monitoring of such environments. In order to be able to download such data, of course you need to, to access the web portal of ESA. You have to create a free account to register and to be logged in, to find the area of interest, to search some parameters that we need, such as the cloud coverage of the our data that we will download, the satellite, the date, etc. Now, some things about the Sentinel-2. Of course, it's an Earth observation mission from EU and Copernicus program. The spatial resolutions are from 10 to 60 meters depending on the band. There are currently 4 bands that offer a spatial resolution of 10 meters. That is really high for considering we're speaking for an open access and satellite with good also temporal resolution. And these are the different levels and products that we can acquire from Sentinel-2, level 1C and level 2A. Level 2 is bottom of atmosphere product, meaning they are already performed some atmospheric corrections to the products, whereas level 1 are top of atmosphere radiance values. So at this point, we also need to mention Earth Explorer as a different repository of satellite data from the USGS and NASA. And from this repository, we can acquire time series satellite data from Landsat missions that are, again, some other multispectral sensors. The Open Access Hub of ESA is this one. So if we click here, and of course we're logged in. I have already my credentials saved for this browser, so currently I'm logged in. We can create an area of interest and then set here the parameters such as the sensing period, the satellite we want to get data from. This is the Sentinel-1, this is the Sentinel-2, and this is the Sentinel-3. And also we can put some other parameters such as cloud cover, etc. So when we have our hands on some data, the problem is that we need to find as much as an automatic procedure to deal with them. When we download the Sentinel-2 granule, commonly it is a zip file, a compressed file, and then we need to extract this file, and then we need to find the data we want, the bands we want, in order to make use of the critical and significant information we need. So all these applications can be done using either scripts or remote sensing applications. Such an application is AirDAS Imaging software. I'm currently opening AirDAS Imaging in my second monitor, and I will demonstrate today an automatic procedure on how we can create a spatial model that will get files, directories in which we have some. Here is the workspace of the software. Directories in which we have downloaded Sentinel-2 data, and then we will proceed with an application, a spatial model for the coastline extraction. First of all, for those who are not familiar with such software, this is the workspace of AirDAS Imaging, but what we're going to do today is we're going to create a spatial model workspace, a spatial model editor. In a spatial model editor, we can create components or subcomponents of the whole of our work plan. So we can imagine this workspace as a piece of paper where we draw the components and we make connections of our work plan as we have it in our mind, and then execute this work plan in order to achieve the desired result. So, for example, to make things easier for you, let's say we want to input in our mind a raster, and then we want to make some process, and then we want to result again into another raster output. This would be just drag and drop this operator, which is called raster input, and again drag and drop an operator called raster output. And if, for example, a remote sensing index, such as NDVI or something else, was the intended process for our input image, if we search here for the operators menu for index, apply index, we can see that this operator has three input fields that needs to be filled, such as raster. So we need to perform an index on this raster, on the input image. So we connect this connection, and the result would be a new image to be created. So it would be the raster output. This is a small example for you to understand how the connections are made. Of course, it is not possible in such a short time to deliver a full training of how this works. But what I'm going to show you right now is the already made applications that I created for the Epipelagic project. So firstly, I created spatial model. It is something like that. But what it does, we feed a Sentinel-2 directory to the program, and then merges a set of different bands, automatically finds the string extension of the file that I want reflects to a specific band. Then we crop these bands to a smaller area of interest, because of course the raw downloaded data have a much more bigger area that they cover. And then we perform for the bands that have smaller spatial resolutions of 20 meters or 60 meters, we perform a warping technique, a resampling technique, to bring it all together via a nearest neighbor algorithm to the 10 meters. And finally, we stack these different bands, to a new raster output image. So by also connecting some ports that are these purple-like buttons, operators, to our model, what we do is that we create a small application. So this is the executable of this spatial model. My initial bands are in the folder inputs. We will see some of these. Let us see. Let's say in a different environment, we will open a 2D view for that. And let's see the band number 2, that it is the blue band of the Sentinel-2 multispectral instrument. This is the whole region of, this is the extent of the raw granule of Sentinel-2. If we also put a base map, an OpenStreet base map, we can see that this is a big area covering a lot of part of central Greece. And we can also see that a specific area of interest that we call AOI, it's this file called Polygon that I just drag and drop into the software, is a smaller area that we need to perform our analysis. So if our program works well, it's going to fuse all these different data, these different separate bands. It's going to cut it to this area of interest that we have indicated, and all the different bands that comes with different resolutions, the band 5, 7, and 11, we'll put it also in the resolution of 10 meters, and then we're going to create a multispectral composite of 7 bands. So this is the work. If we run this model, what we want to just indicate is the area of interest. It is an optional parameter, but at this time we need to create smaller area of interest. So we can define this either if we have an open AOI in our viewer that we don't at the moment, or by just showcase the directory in which we have our AOI file. In this case, it's here, so we select the AOI. We also select an output. I have already performed earlier this application, but I will just replace the image, and I will also select just the path in which there are some Sentinel-2 JP2000 files. In this case, I need also to mention that this spatial model works also in subfolders. So if you just unzip the folder that you have downloaded from the Sentinel Open Access Hub, the model will find also will crawl inside the subfolders in order to find the extension that we have mentioned. So we can see with the green tick check mark that the model runs smoothly, runs well, and it is currently finalizing the output. And in such short time, it has created a new multispectral composite in the directory that I indicated the software to create it. So if I create a new 2D view and just navigate to the output folder and drag and drop, you can see that it is today's date. Drag and drop this image. We can see that indeed it is the smaller area. If I put also the base map again, the Epipelagic base map, I can see that it is the smaller area of interest, and it is indeed a multispectral image with 7 different bands. And again, I can create with this an RGB natural coral composite. This is the city of Kardica, and this is the central mountains of Greece. So this was the first example of how we create the data, and let's just continue with how this multispectral data, by exploiting this multispectral data, we can create a coastline vector of our area of interest. Of course, we're going to use different data for this because we need a coastline. So the next scenario is go to the coastline extraction. For this, we have created 3 different spatial models. Of course, I need to have a shout out on that to the publication reference. The original spatial model is published on the community hub of the spatial community of Hexagon, and also was dealing with coastline from Worldview 2 and 3 satellites. But what we slightly shifted the model, and what we do is that we made it to be able to run it also with open access free data, such as Landsat 5, Landsat 7, Landsat 8, and of course Sentinel-2. So again, really quickly, what this model does is that exploits the bands number 8 and number 3 that produce an NDWI index, a new raster NDWI, and then produces some thresholds that the water is more likely to be found. Then non-supervised classifications with 3 classes and isodata algorithm is performed in order to create a thematic raster output. And then by some other parameters and thresholding, we just lead to vectorization of the raster. So we just take the boundary between the classified land and classified water, and we take this boundary that it is a vector file, and we create this vector file. So in a nutshell, this is, and of course the output will be a feature at this time. It will be a feature. This is the output. So for this instance, I have some Sentinel-2 data that are here. Again, these are multispectral Sentinel-2 images of an area of interest. And if we run this, again, the results, what we we put some inputs is only the Sentinel-2 imagery and only the output of the features. Typically, we can put some other parameters, but at this point I will not. The result of such application would be some lines, let me vector lines of our area of interest. So if we also add the initial data and the corresponding vector lines above them, we can see that the respective timeline produces significant results even in challenging environments. We can see that with a really good reliability, in my opinion, we can produce effective vector lines for the coastline. Again, a different timeline would be, let's say, the 11th of October 2019. That it is this one. And again, we can see that we can deliver with really good accuracies the coastline extractions. Even in times when the river has a lot of turbidity and suspended matter at the coast, the algorithm is good enough in order to distinguish the land between the water. So if I rerun it, because we didn't before, what we just need to include is the Sentinel-2 output, input image. Just to be sure that I'm in the correct folder, Coastline Extraction, Sentinel-2, and get an image. All the other parameters are not necessary. And we can see that the whole work has finished. And that today, the 25th of September, this vector line was created. In order to perform batch processing for multiple files and for multiple locations, what we can do is we can run this model in a batch. So in the new window that pops up, we can select to add multiple Sentinel-2 imageries by clicking here and putting add files, and then create this whole data set of Sentinel, and then by just clicking run, we can get the model to run several times. So I will close now this model and I will open a different software that it is the Quantum GIS, the QGIS, in order to see how we can view the results also into the Quantum QGIS and probably create some really interesting visualizations of our coastline data. So I'm closing Curtis Imaging. Thank you very much for your help. And I'm opening Quantum QGIS. This is typical a typical environment of Quantum QGIS. And what I'm going to do here is I'm going to include all the vector lines that I have previously created. What I'm going to show you is how we made temporal views. So we know that this line refers to the 17th of February of 2020. So what we can do is by putting by right-clicking properties and by putting a temporal fixed time range to this line, we can assign it to the 17th of February of 2020. So this will do it. So you can see that I have a specific time range. The hour it isn't really important of this data set, and you can see that also this layer is a temporal layer. If then we're going to open a temporal control panel, we can make videos and snaps of different how the different layers are producing and developing through the time. We don't have much time to do this for the whole images, but I will show you a really nice GIF that I have created with this methodology for a previous publication, and this is actually for the Epipelagic case study. You can see on the bottom right of your screen how the time develops through multispectral views and how the coastline develops again through this time. You can see the changes between each semester because these views were semester by semester, so the changes between winter and summer are really significant, or probably from April to October, that were the instances coming from, are really significant year by year. But to this end, we can of course create our customized GIFs by setting and selecting data, let's say each month or each year, and creating our own maps to be able to monitor, to effectively monitor coastline changes. So moving on to this end, we already dealt with developing autonomous ways of developing multispectral composites, and also via spatial modeling, and also creating a model for the coastline recognition and extraction. We just set some inputs, and all the process refers to the WI calculation, supervector classification, water bodies identification, and a final layer of vectorization to a shape file that represents the coastline. Now we will see some ways in order to develop coastline extraction methodologies by using a big amount of time series data, a vast amount of time series data, to be honest. Okay, first of all, I would like also to say that we also tried this publication and the coding framework with Python that uses a similar procedure to what we presented earlier. We also tried it to our area of interest and put some interesting result. But what we also intend to add to the Epipelagic case study is to add also Sentinel-1 data to the loop and trying to exploit the different reflectance of the signal in Sentinel-1 bands. And also to, as I said also in the presentation, the beginning of the presentation of the project, to create, to exploit advanced deep learning techniques in order to further improve the results, such as the self-attention transformers. Later on, these are the data, the Landsat data that I will demonstrate in the next example with Python. So we use data from the year 2000 until 2020, 2 years of 20 years of data, and you can see how the vast amount of different captures that we deployed. To this application, not this one, it's this one. I'm going to briefly show you our Python script. Of course, this is currently under evaluation for a publication. So briefly, I will describe what it does. It actually gets the user actually indicates the script, and we can probably run it also in an environment, a Python scripting environment. The user showcases a directory where time series Landsat data are again downloaded, and then only gives a shapefile area of interest in which we again need to crop this remote sensing satellite data. After that, all the procedure is automatic, and by producing atmospheric correction, cloud masking, and unsupervised classification with k-means algorithm, we can get exactly a binary map with what is land and what is water. So at first we're going to see such operation. These are some statistics for the bands that were used. This is the clipping procedure, and afterwards the atmospheric correction, and this is the result of an atmospheric of a k-means supervised classification at the end. So I have opened a Spider environment. And I'm going to run the file. So at first, the program needs me to showcase where are the Landsat data. They are in this folder, so I just click indicate this directory. And secondly, I just need to indicate the study area. The study area is here. Inside these are the zip files of the area of interest. And okay, probably I needed to use it in a different environment. Anyway, it wasn't intended to run it now, the full program. The results of such operation are created differently inside this folder. A different folder is created for the atmospheric corrected bands, a different folder for the clipped atmospheric corrected bands, and the correct reprojected CRS, that it is the 2100, that it is the national Greek grid. And finally, we have a composite of the classification of the whole dataset. This dataset is just one one capture with the different bands, and this results to a classification map. If we drag and drop this classification map to the quantum QGIS, we can see how well this algorithm actually works, and how we can distinguish the water and non-water of this on this specific instance. I will also add a base map for you to be able to better see the result, and I will also exploit the swipe tool of QGIS, and you can see how well we have identified what it is water and what it is not. So this is already a good step to develop such an application, but in this project, what we also need, and why it is important for us to see the dangers of the coastline, is by monitoring the specific case study for multiple instances and for multiple years. So the purpose is to analyze information for decades, because the dangers for such sites is that they're slightly evolving, and that the scientists and the engineers, we should be able to identify these dangers by monitoring time series data. So a really good advancement to this is that we have created a time series map. So the next script that we have developed is analyzes the first results, such as the one that I demonstrated right now, and create mean maps of the mean values of each pixel, and thus we can understand which is the probability for the last 5 years, let's say, of each specific pixel on the map to be flooded or not, to have water or not. So some pixels, such as the ocean, or such as the beach, the sea near to the beach, will be constantly water, and in some cases also around the mountains or on the slopes of the mountains will be constantly land. But there, in these environments, challenging environments, there will be some cases in which some pixels will have a probability, a high or low probability to be flooded or not. So the good advancement of this application that I'm showing you right here is that we have created for a specific year, by using all the time series data of this year, but also for a period of different 5 years. So the 5-year interval of 2002 and 2005, the 5-year interval of 2006 and 2010, etc., etc. We have created, let's see the final 5-year interval. We have created this map. So this is really important. We can also in QGIS put different symbology. So if I create a single color band and pseudo color single band, and if I invert this color ramp and probably classify in equal interval, we can see a good result on which is the probability of each pixel to be water or not. So of course some wetlands and the river basin will be constantly water, but there are some regions such as these or these that are flooded and in specific scenarios. So by analyzing the differences between these different 5 years intervals, we can give to the stakeholders really crucial information in which areas are vulnerable and which are the changes of the landscape through the year. If there are any questions on that? Anyone? I will also present some differences between the years. So we can see the new waters and the receding water bodies for our area of interest. And we can also see some flood map for the 5-year interval, as I also demonstrated previously. With low probability of flood, high probability of flood, and the general water bodies that are constantly distinguished as water. These are the probability for the period 2005, for the 10th, and for the last 5-year period. So again, we perform the same techniques with Sentinel-1 and Sentinel-2 datasets. And finally, I will also show you here through the presentation, because we don't have much time, an application with Snap software. Snap software is this one that I will open right now. Is from the European Space Agency, the Sentinel Applications platform, developed for exploiting and analyzing and using Sentinel data. This is the interface of the platform. Of course, it has various and diverse capabilities. What we did, though, is that through optical and thematic water processing, we ran some C2RCC processors for Sentinel-2 MSI instrument. And what we did there, I will open this environment, we ran this operator for analyzing the chlorophyll A parameter and total spatted matter parameter for our area of interest for the years 2019 and 2020. So again, these were the datasets that were acquired for this application, and with the Snap software, we perform this pre-processing application, these pre-processing techniques. First of all, we sample the data to the 60 meters, not centimeters. This is wrong. Meters as pixel size. We also subset the area of interest to a smaller region for our use. And we opened the C2RCC application as also illustrated here. What you want to do now actually is you want to select the L1C product, and then what you want to do is also put some empirical parameters here for you to find the salinity or the temperature of the water. You will need to get as much as reliable information. Of course, it doesn't need to be exactly the same as in real life, but you need to be close to your water you want to analyze, your water body you want to analyze. So a good way to get such values in relation, of course, to the time that you're performing, the time period that you're performing your analysis, is by, if you don't have in situ information, in situ measurements, you can get such information from from the marine ocean projects, from the marine Copernicus service of ocean, or you can, for salinity, for example, it's a good example to get the Mediterranean Sea in situ time observations, or you can get for salinity, or you can get for the sea surface temperature that also need to be put in Snap software, or you can visit the state of the art from JPL laboratory in NASA, and again you can add this is the sea surface temperature for the Mediterranean Sea, or we can put something different such as sea surface salinity. Let's put everything here. So you can see that this is the sea surface salinity. So these are examples, empirical examples that you don't get exactly the value you want, but you get an idea by seeing also this legend here. You get the idea of an empirical value that you will want to add to these parameters, to these fields. The result of this again were some maps of the chlorophyll A and the total suspended matters that we again created two different layouts. Again, by opening QGIS and by navigating to the Sentinel-2 biomass, we can get either the total suspended matter or the chlorophyll A. Let's show this image, for example, and by again creating different color map, we can see the different realities in the different waterlands in our area of interest. We can see significant changes here, here, and here. So we also put a total suspended matter result. You can see it slightly different because we analyze a different parameter. It is for the same it is for the same instance, from the same data set, a map showing the total suspended matter of the area of interest, and the map showing the chlorophyll A again in this area of interest. So I believe that was it from me, from my part. I tried to be as to present as briefly as I could all the application in order for you to get an idea on how we can use open source data and open source or commercial technologies in order to perform some applications. Of course, some applications are more challenging than others, but of course, the concept of this festival is to bring together different actors of the Mediterranean Sea and to see how we can use information that different actors have acquired in order to produce finally important applications and important knowledge for the preservation of the ecosystems in the Mediterranean Sea. If there are no questions, thank you very much for your attendance. And again, it was a pleasure from me personal, but also from G-Systems and us to be part of this festival for the Mediterranean Sea. Thank you very much.